Okay, she's recording, so I better be careful now. All right, well, we will go ahead and get started. Thank you so much. This is April, I think. Time has been a little bit crazy. Oh, somebody raised their hand. Oh, I guess, Donna, this is actual webinar format, right?
It is. So maybe put questions in the Q&A or the chat and we can.
Yeah, thank you. Yes, please put questions in the Q&A or the chat, as Donna just said, and we will monitor those. And Joe, do you want me to interrupt you if there's questions or?
Yeah, I guess so. I guess so. That'll be fine.
Sounds perfect. Okay. And Joe graciously agreed to, first of all, give the talk today and also let us record it. I'm a bit behind in posting things to our R Govys channel. So I think this will be my third month that I'm behind. So once Donna sends this to me, I'm going to get these posted. And I just want to, before I pass it along to Joe, I just want to let folks know about the Use R conference, which is in August. It's right, I think, after the joint statistical meetings. So if any of you are going there, you could kind of swing by maybe Duke University, which is where it's going to be. But I found out that there's a sort of a satellite virtual event that's going to take place the week before. And it's August 1st, I think, which is the Friday. I don't think there's necessarily registration for it. It seems like they're going to be streaming it, or it's going to be on their YouTube channel or something. So anyway, you could go to, I think it's like Use R 2025, or if you just kind of Google it, you could find information. But for those of you who come to the interagency R users group, I'll pass that information to those folks. So, and maybe if while Joe's talking, I'll multitask a little bit and I'll put the link to that in the chat while I'm still listening to Joe's talk. So as usual, I'll let the speaker introduce themselves, but I'll just say that I've had the pleasure of knowing Joe for many years and working with him, not super closely because we've been remote until recently, but working with him as a fellow census colleague. And so I've really, really enjoyed interacting with Joe and especially learning from him. So that's what we're here today, to learn from Joe. And I'm just going to let you take it over. You could introduce yourself and talk about your latest, your package, bigLC, right?
Yes.
Great.
Is this visible?
Yep, I see it.
Okay. So thank you, Wendy. I see some familiar names and faces in the attendance list. I wanted to say a special hello to Eve Thibodeau. And I know that I owe you a response to the email you sent about several days ago about this package. And I'm going to answer your question directly at the end of the talk. And to the rest of you, thank you for being here. So I actually spoke on this package when it was in its very early stages of development. I think it was about a year ago, and a little bit less than a year ago. And now it's mature enough to almost be ready to post on CRAN, so it will be appearing there shortly. I'll give you a little note on that in a moment. And this document that I'm going through today is a Tufte handout. I decided to follow Ed Tufte's advice and not use PowerPoint, but instead prepare a handout, which could be something like class notes. And I'm willing to share this document with anyone who's interested. I sent a copy to Wendy, and so you could get it from her, you could get it from me. So let me just explain what I'm talking about. So bigLC is a new R package that fits latent-class models with an emphasis on prediction and imputation. So this is not like traditional latent-class analysis. The difference here is the classes are not intended to tell a story about groups in the real world. Their purpose is mainly to make the model flexible enough to conform to strange features in the data without any extra input by the user. And traditional latent class analysis tends to use categorical variables only, but this model accepts categorical, continuous, semi-continuous, or integer count variables. And the data may also have arbitrary rates and patterns of missing values. Another big feature is that it accommodates multi-level structures where observational units are nested within larger units. For example, if you have persons within households and maybe households within census blocks or tracts and so on. And you can have missing data at any level. The user selects a distributional family for each item, sets the maximum number of classes for each level, and then lets it go. That's the extent of fitting the model. And there are two fitting methods. There's an EM algorithm for maximizing the likelihood, and there's a Markov chain Monte Carlo procedure. I'm going to mainly focus on the EM algorithm today, but MCMC is very easy to use, and it's sort of a trivial extension in the software. In the function call, you just change the method from EM to MCMC, and away you go. I will mention that this group made some very good suggestions last time I presented this. And so based on partly on the R Govys group, I expanded and enhanced this work. As I mentioned, bigLC is undergoing final review and cleanup for submission to CRAN. And if you would like to try the package sooner, please contact me and I'll send you a version that you can install. Okay, so what does this do? bigLC describes multivariate data through latent class models. The latent classes, as I mentioned, are intended to make the model flexible to conform to special features in the data without a lot of tuning by the user. The items may be categorical, continuous, semi-continuous, or integer counts. The input data can have missing values at any level. It accepts multi-level data, and there is no inherent limit on the number of levels. But once you get beyond 3 or 4, it's hard to actually imagine how the model is working, and it tends to take up a lot more computational time, depending on how many classes you've got. But in theory, you can have any number of levels. And there's also no internal limit on the number of variables or the number of observations per level. To specify the model, you choose the items to include, you set the distributional family for each item, and then you set the maximum number of latent classes. And that's all. So people who are trying this out are saying that it's quite a bit simpler than the fully conditional specification or FCS methods used by mice and IVE-ware, because those require you to define a regression model for each item given the others. So you've got to specify lots and lots of regression models. It's also simpler than a set of hot decks, because hot decks require you to define donor pools for imputing each incomplete item given a set of observed items, with rules for enlarging the pool when it is too small. Now, one reason why I'm mentioning hot decks is that there is an intuitive connection to the hot deck in this method, which I am going to hopefully explain and make clear. But once you've specified the model, you fit the model using EM and Markov chain Monte Carlo, either or. And I like to use both, actually. So EM climbs the likelihood function to find a solution that fits the data well. And MCMC relaxes the EM solution and explores the posterior distribution of the unknown parameters. And that's how we reflect uncertainty. And then after fitting the model, you can take the fitted model object and use it to generate predictions, single or multiple imputations, and even synthetic data. I'll give you a very brief background on latent class analysis. LC analysis was originally developed to synthesize responses from multiple survey questions. And it originated in sociology. It also has been used quite extensively in medical and psychiatric diagnosis, and also for estimating rates and patterns of response error in censuses and surveys. This work that I began working on about a year and a half ago, was inspired by some papers written by Vermont and his colleagues, and also Jerry Ryder and his colleagues, who proposed using predictive latent class models as an imputation engine for multivariate data. And the essence of an LC model is that it takes a bunch of variables and it describes their joint distribution by supposing that the population consists of hidden groups. We call these groups the classes. And the word latent means you don't see them. You don't know what group each unit belongs to. So they're hidden, they're latent. And you assume that within each group, the observations follow a simpler model than the population as a whole. And specifically, what we are assuming is that each item follows a simple parametric family, categorical, Poisson, normal, and so on. And within each group, the items are mutually independent. So then once you marginalize over the groups, each item is then a mixture of the simple parametric family. So for example, a mixture of Poissons, a mixture of normals. And because of the independence assumption within classes, once you average out the classes or marginalize over the unseen classes, you get relationships among the items. As you increase the number of hidden groups, the models tend to fit the observed items better and better. And eventually you reach a point of saturation where if you add more classes, you won't really make a difference because the extra classes are redundant or empty. Redundant means they're essentially copies of existing classes. And so you're just splitting one class into two when they could be collapsed. Or the extra classes have so few cases in them, they're essentially empty. The probability or prevalence is zero. If you want to think about machine learning, what bigLC is doing is soft classification. It's doing fuzzy assignments of units to classes with probabilities. And then in order to find the soft classification scheme, it's using an unsupervised learning technique where it's taking only internal evidence of the data. You don't have any access to a training sample where the groups are already labeled. So it's unsupervised learning based on the current data set. Here's a very quick example of a traditional latent class model. In the general social survey, there is a panel of items on attitudes toward legalized abortion. And this has been going on since for decades, actually, so that sociologists can track changes in opinion over time. And in the year 2000, which is the year I decided to look at, there were 7 specific questions. So the topic header is, please tell me whether or not you think it should be possible to obtain a legalized abortion if, and then there are these 7 specific cases. If there's a strong chance of serious defect in the baby, the woman is married and does not want any more children, and so on. The possible responses were yes, no, and don't know. And by design, all 7 items were missing for 1/3 of the survey participants because they used a matrix sampling scheme with 3 different questionnaires. And so 2/3 of the survey participants got these questions and 2/3 and 1/3 did not. Now, if you look in media reports, you often see labels on positions such as pro-life and pro-choice, but published analyses going back to the 80s have shown that people have tended to cluster into at least 3 major groups. And so there's a series of papers by Alan McCutcheon where he looks at, he tracks these 3 groups over time. There are, in reality, more than 3 different opinions you can have, but the 3-group solution is pretty robust. It tends to show up year after year. And these are the 3 major groups that you see in the population. So I fit a 3-class model And I got the parameters that I'm showing in figures 1 and 2. So in figure 1, we see the estimated percentages, or the so-called prevalences within the classes. So I ordered the classes 1, 2, and 3 from most prevalent to least. And then to describe the character of the classes, I looked at the probability of answering yes, the estimated probability of answering yes within each of the 3 classes. So the black bar, which is class 1, has a high probability of answering yes to certain questions and low probabilities for others. Let's save that for a moment. Class 2, which is about 36% of the population, tends to support legalized abortion for basically any reason. So the gray bars are high consistently for all 7 items. Class 3 is consistently low. It's this light colored bar. It's consistently low for all 7 items, except possibly the health of the mother, which is a little bit higher than the others. So this most prevalent class, which I'm labeling class 1, tends to support for what you could call medical or ethical reasons, but not for other reasons. And so, as I said, this is a fairly robust finding. It doesn't fully describe the population. You can see that these probabilities, these item response probabilities within the classes are not 0 and 1. So within each group, there's some heterogeneity, but some are close to 0, some are close to 1. So they tend to pick out groups that have similar response patterns. If you're interested in the R code for the analysis, this is what it looks like. So the bigLC function fits the model, and the first argument is a model formula. It's a one-sided formula with the items that you want to include in your model on the right-hand side. I don't have to declare a distributional family for any of these because the default is a categorical family. And so because all of these are factors, it just fits categorical families to each one. The second argument is the number of classes you want, and I'm calling it the maximum number of classes because the classes are not necessarily filled, but here I set it to 3. And then the third required argument is just the data frame containing the responses. After fitting the model, there's a bunch of functions that you can use to extract information. There's a summary function. There's functions for pulling out the class prevalences, which I plotted in figure 1. There's a item params function for pulling out the item response parameters that I'm displaying in figure 2, and so on. And if you're interested, at the end of this document, I have an appendix that just lists the main functions and what they do. Now let me give you an explanation of some of the important terms that I'm going to be using today. So the unknown parameters that need to be estimated in this model are 2 types. There's the class prevalences, which are the relative sizes of those hidden groups, and then the item response parameters, which describe how well each item or how each item is distributed within each class. So taken together, those are the unknown parameters. The log likelihood function measures how well a set of parameters fits the observed data. And so this is the objective function that we're going to be using to search for a good solution, a good soft classification scheme. Good parameter estimates are those with high log likelihood. They fit the data well. And if you know anything about latent class models, you probably know that the log likelihood resembles a mountain range. There's tends to be multimodal. There are high peaks that fit the data well, and also shorter peaks that fit less well. And because of that, you probably want to run the EM algorithm multiple times from multiple starting points because you don't want to get caught in a poor fitting solution, and that can sometimes happen. EM finds the solutions. It will converge to different solutions depending on the starting values. It only knows how to climb. It's kind of like a short-sighted mountain climber who will never follow a path that descends, even if that path would lead to a top of to the top of a much higher mountain peak nearby. So EM is only trying to go up. And so for that reason, it's a good idea to try different random starts. After you reach a solution, we have what are called posterior probabilities. You can think of these as soft classification rules. And you can think of this as a matrix with rows corresponding to the records in the original data set and columns corresponding to the hidden groups. And there are probabilities in this matrix. Each row adds up to 1. It shows the estimated probability that that record belongs to each of the groups based on that record's observed items. So this is the soft classification scheme. Once you reach a solution, bigLC will take these posterior probabilities and it will randomly draw a class membership for each record. So in addition to that soft classification, it will give you a random hard classification. And I find that can be very useful for diagnostic purposes. It can show you how the model is grouping together records that it believes are similar. And so if you start poking around in these classes, you can see what the groups look like. And you can think of them also as donor pools for imputing missing items. And I'll explain that a little bit more fully. They're not real donor pools because you're estimating a distribution for each item within each latent class. So the number of available donors is infinite. This is a model-based method. But you can think of those classes as defining donor pools for a simple item-by-item imputation, because within those classes, the items are assumed to be independent. I'll briefly mention now the distributional families. The default is categorical, and there is no upper limit on the number of categories. Another family you can use is the Poisson family. It's good for count variables with possible values 0, 1, and so on. But I also have an optional shift argument that allows you to move the distribution over by a fixed amount so that it begins at an integer other than 0. So for example, suppose your units are households or occupied housing units, and one of the variables you're modeling is the number of persons in that unit. Because they're occupied, the minimum is 1, so you'd want to use a shift of 1. Now, just to clarify, if you say Poisson family for an item, you're not assuming that that item has a Poisson distribution. You're actually assuming it's a mixture of Poissons, mixing over the classes. So it doesn't actually have to resemble a Poisson. It can be over-dispersed. But if it's severely over-dispersed, you might want to switch to a negative binomial. That's also good for count variables, but it tends to describe upper tails a little bit better. And it also has an optional shift. If you're working with continuous outcomes, there's a normal family. This works for continuous variables that are not highly skewed. There's a variant of that I call func normal that assumes that it's normal within each class after applying a transformation. And the transformations now that it will accept are log, logit, and also the identity if you don't want any transformation. Another nice feature of this func normal family is that it also has an optional point mass argument that allows you to insert discrete outcomes at specific locations to make the distribution semi-continuous. So, for example, if you have an income variable that's a mixture of zeros and continuous positive numbers, you can model it as log normal within classes, but then put in a point mass at 0 to give it that two-part feature. Those point masses are also good for top codes, bottom codes, and other special values indicating that a response is out of range or an item is out of scope. And then the last family is the gamma family. I like to use that sometimes. I find that it fits better than the log normal. Sometimes it fits worse, but sometimes it's better. And this also has a point mass option. So you can model your income variables using a gamma family with a point mass at 0, if you like. Let me show you a couple of quick examples of how bigLC is allowing you to pick up unusual features in the data without having to tune it very, very much. So this plot that I'm showing you in figure 3, some of you might have seen this data set before. It figures very heavily in the book on semi-parametric regression, and it's included in the semi-par package. It is a bivariate data set with 2 continuous measures. The x variable is the age of a fossil in millions of years, and the y variable is the strontium ratio. Not sure what that is, but that apparently is closely tied to the age of the fossil. And you can see that there is a pattern. There's a very nonlinear relationship here. What I'm doing here is fitting a bigLC model to this bivariate data set, setting the family for each of these to be normal. And so the way to set the family is before calling the bigLC function, you call this function called LC item, which you can think of it as a preprocessor. What it does is it takes the item and it assigns a family attribute to it. So you basically pass the item through this LC item function. It doesn't change any of the data values. It just attaches attributes that are later recognized by the bigLC model fitting routine. So I set the 2 families to normal. I set a random numbers generator seed, and the reason is the EM algorithm is using random starting values, and so if you want to reproduce this, you should set the seed. And then I just fit the model. I put in the 2 variables. Here I set the maximum number of latent classes to 12, and that took a little bit of playing around. I'll tell you what I did. I first started at 10, then I increased it to 12, and I found that the smallest of the latent classes was pretty small, and then I tried 15, and some of the classes were essentially empty. So I decided to stop at 12. If you stop at 10, you don't get much of a different fit. And if you stop at 15, you don't get much of a different fit. They're all pretty close. So I ran the EM algorithm 3 times. And what I'm showing you in this figure 4 is a plot of the 3 log likelihood histories over the first 50 iterations. So you can see by this plot that you're starting at different places. So the log likelihoods at the start are different, but then quickly it rises and then they get very close together. And after about 20 iterations or so, the plots level off. So at that point, the log likelihood is not increasing very much at all. Now the parameter estimates are still changing. What's happening is each run is marching toward its solution, but because the log likelihood is very flat in the direction that it's moving, you don't really have to continue very long before you're getting a good fit to the data. So what I did here after this was I took one of the fits, I took the 3rd one, and I extracted the imputed classes. So I mentioned to you that after running the EM algorithm, it automatically draws classes for each of the units in your data set. So I grabbed those classes, and then I set up a plot where I plotted the observations with different plotting symbols to show you the different classes. Then I also created an X grid, a grid of X values from 90 to 125. And along that grid, I used my predict function to extract predicted values, expected means for the Y variable, given that specific value of the X. And that's the fitted line that you see. So this is a little bit more wiggly, a little bit more choppy than a smooth semi-parametric fit that you get from, say, a generalized additive model or a smoothing spline, but it's pretty close. And one interesting feature of these models is that at the extremes of the data set, it doesn't veer off in a linear direction. It tends to become flat. So these models won't really interpolate for you, or sorry, extrapolate. They're not designed for extrapolation, but if you were to use them for a little bit of extrapolation, the extrapolating function is essentially constant beyond the convex hull of your data set.
Hey, Joe, could I
Sure.
interrupt with a question?
Sure.
So the curve that you just created, is it possible, or have you or others done like developing confidence bands, I guess I'll say, around the curve?
Yeah, so bigLC does not give you any standard errors. The reason why I decided not to put any standard error calculations in the procedures is that these classes tend to be very fluid. They're as you fit different solutions, the meaning of the classes tends to change, and so the actual parameters of the model, the standard errors, it's not sure what they mean sometimes, because once you start expanding beyond or getting far away from your estimates, what happens is the meaning of the parameters and the meaning of the classes starts to change, if you catch my drift. But there is a way to do what you suggested. And the way to do it is to run Markov chain Monte Carlo. And if you were to take, say, if you were to run MCMC, say, do 100 short runs beginning from this EM solution, that's very easy to do. And then you could run this predict function on each of those solutions coming out of MCMC, and then you plot the band formed by those 100 curves. And I've done that quite a lot, and that works pretty well.
That's a really cool idea. Yeah, thank you.
In fact, I was going to put that in. I was also going to put that in for the sake of time. I didn't, but I was going to show you what this curve looks like, not from the single EM solution, but what it looks like if you took, say, those 100 MCMC curves and averaged them, which gives you the estimated posterior mean of y given x. And that it is quite a bit smoother, and it tends to look pretty much like the semi-parametric regression curve fit to this data set. The only difference is at the extremes, it becomes constant rather than continuing off linearly, like those semi-parametric fits tend to do.
Very, very interesting. Thank you.
Okay, thank you. Now I'm going to show you how bigLC imputes. Suppose this example is a little bit contrived, but bear with me. Suppose somebody gives you a new fossil and tells you, hey, this fossil is 101 million years old, but I didn't send it to the lab yet for the strontium ratio, so I don't know what the strontium ratio is. Can you impute the strontium ratio for me? Well, okay, so at 101 million years, we know that this new observation lies somewhere along this vertical line, this dashed line, but we don't know where. So what I did was I took my EM fit and I created a new data frame that has age equal to 101 and no value for y, no value for the strontium ratio. And I replicated that 1,000 times so that I could get 1,000 imputed values, just so you can see what they look like. And then I passed it to my impute items function, and I got a new imputed data set. And if you take this imputed data set and just look at the strontium ratio, look at a histogram, what you see is that all of the imputed values for y here are at the high end of the scale. So what's happening is the algorithm uses x equals 101 to make an educated guess about the hidden cluster to which that new fossil belongs. And it says, oh, it's in one of these it's in the clusters that tend to occur over here. If we go back here, we see that depending on the EM solution, that cluster could be this one. It's anywhere around here. So, but it makes an educated guess that it's probably there. And then it uses the estimated distribution of Y in that cluster, which is a normal distribution, as the donor pool for imputation. And because that method is model-based, the donor pool is infinitely large. So these are the imputed values, and looks like this range up here. Now let's do the other thing. Let's say, suppose somebody gives you a fossil with a known value of Y, but an unknown value of X. Okay, so we know that the Y is up here. We know that this new observation is somewhere along this horizontal line, but we don't know where along the horizontal line. So I'm doing the same thing. I'm creating a fake data set with that value of Y and no value of X. Putting in 1,000 rows so we can get 1,000 imputed values. And the histogram of the imputed values looks like this down here. So knowing that value of Y is up here, we see that there are probably at least 4 hidden clusters to which the fossil could belong. A cluster over here, a cluster over here, a cluster over here, and a cluster over here. So for each draw, the algorithm is selecting one of those clusters with the appropriate probability from the matrix of posterior probabilities. Then it's using that selected cluster's estimated normal distribution for X as the donor pool. And so you get this nice multimodal imputed distribution or predictive distribution for X. Okay, so that's a relationship, a complicated relationship. Now I'm going to show you how bigLC can fit a complex item distribution, a complex marginal distribution. So this histogram over here is the distribution of age for persons in the Ohio 2022 ACS PUMS, the American Community Survey Public Use Microdata Sample, which is roughly a 1% sample of the Ohio population. So about close to Ohio had about 12 million people, so it's close to that. I took out the group quarters persons, so these are only persons in housing units. And age in years ranges from 0 to 94. There happened to be no observations in the sample at 91, 92, or 93, and 94 was used as a top code for this state. So that's why you get this spike over here. It represents 94 and older. So what I did was I fit 3 different models using different families. After each fit, I then simulated a new completely synthetic version of the variable to see how well it reproduced the distributional shape. So let's first start with a default categorical family. So this treats every year as its own category. So there's 94 different categories, but there's nobody observed at 91, 92, or 93. So those years are going to be empty. If you do this, the fit is excellent. However, the number of item response parameters is large, and so you probably don't want to use this. Now let's try a Poisson family. With this imputed family, the imputed values have no hard upper limit. And the spike at 94 is going to get spread out over the upper tail because that 94 is treated as an ordinary observation instead of a top code. So you get a similar shape to the main body of the data set. You still see the baby boomers up here that bulge, but the spike at 94 gets spread out into a tail. And finally, let's go to the family that I want to use, the func normal. To preserve the upper limit of 94 and the top code, what I did was I shifted and rescaled the values so that 0 to 93 are moved inside of the unit interval. And then I selected a logit transformation, and then I put in a point mask for that top code. After generating synthetic values, those are going to be continuous. So I rounded them. I transformed them back to the original scale, and then I rounded them off to the nearest integer. And so if you do it this way, you get both the distributional shape and you get the preservation of that spike at 0. So, and you have far fewer parameters than you did with the categorical data model. Okay. Enough with the toy examples. Let me go to a real example. I worked up this example to show some people at the Census Bureau in the decennial directorate who are already thinking about how to do the imputation for the 2030 census. 2030 census is less than 5 years away, so we better get moving. This example is intended to mimic joint imputation of the decennial housing unit and person items using data that are publicly available. So there is no confidential data in this presentation. I'm using the 2 housing unit characteristics that show up in the census, the building type, which has 10 different levels. It tells you what type of building it is, whether it's a mobile home, single family detached, single family attached apartment building with how many units and so on. The other is tenure, whether it's owned or rented, and there's 4 levels to that. There's owned with a mortgage, owned free and clear, rented for payment, occupied without payment of rent. There's the number of persons in the housing unit, and then for each housing unit, because these are occupied units, I decided to separate out the characteristics of the householder. The householder is what we call person 1 on the form. Whoever is listed as the first person, that person has an age, a sex, Hispanic origin, and then indicators for the different racial groups that that person can belong to. And I decided to put those in at the household level because you can think of those as household level variables. And then each additional person in the household, if there is one, has characteristics, age, sex, Hispanic origin, and the different races. So this is a data set where the lowest level is the person, the second level is the housing unit, and then I'm going to throw in another geographic level, which I'll explain in a moment. The data that I'm using are from that same Ohio PUM sample. There were 50,000 occupied housing units with those 115,000 persons. And those housing units in the data file are grouped into 90 public use microdata areas, which we call PUMAs. PUMAs are geographic areas that have at least 100,000 persons in them, and they're the smallest level of geography reflected in the PUMs. If this had been actual census data, it would have been much more dense, and I could have used a 4-level model. For example, persons within housing units, within blocks, within tracts. But what I'm doing here is using 3 levels: persons within housing units, within PUMAs. So using the PUM's imputation flags, what I did was I set the flag values to missing. So those items that I mentioned here have missing values. Some of them were imputed. So I decided to get rid of the imputed values. All of the flagged items I set to missing. And then I used bigLC to re-impute so that I could then compare the bigLC imputations to the PUM's imputations. As far as my distributional families, I'm treating the number of persons in the housing unit as categorical. Age, I'm treating as func normal with the point masses that I showed you before, to the point mass for the top coding at 94, and all other variables here are categorical. Now there's an interesting edit restriction here. There are 6 binary race items, and the ACS does not allow you to answer no to all 6 binary races. If you don't choose a race, they will choose one for you. In order to enforce that edit restriction, I used rejection sampling. Now, here's a little note. This is a partial answer to Eve Thibodeau's question to me before. Latent-class models can be formally truncated to enforce these edit restrictions. bigLC does not yet fit these truncated models. So for now, what I'm doing is I'm approximating that truncation through rejection sampling. If I try to impute somebody into that forbidden cell with no race, I reject and redraw. Just to explain how the soft clustering works, the model identifies pumas with similar housing unit and person data and groups them into latent classes at the puma level. Then, within each puma class, it identifies housing units with similar housing and person characteristics and groups them into classes. And then, at the person level, it groups similar persons within each housing unit class. So there are 3 levels of latent classes. There's pumas, housing units within pumas, and persons within housing units within pumas. Based on a little bit of exploration, I decided to use 5 classes for the pumas, 100 for housing units, and 20 for persons. And basically, if you go beyond that, you get a lot of empty classes. This allows persons to be grouped into a maximum of 5 times 20, or 5 times 100 times 20, or 10,000 different classes. So this is a pretty rich model. There's a little note about processing time. I'm going to skip that for now, but it basically took under an hour to do this. Here is the code. In the interest of time, I'm going to skip over this, but I have comments there if you're interested in seeing what it looks like. And then I'll just jump to a few results. What I did here was I compared imputed values from the PUMS imputation, which I threw away and re-imputed with bigLC. And so I'm comparing for each of these items, the values that were imputed by PUMS and the ones that were imputed by bigLC. And the distributions look fairly similar. There are some discrepancies. So for example, bigLC is imputing far fewer huge apartment buildings. I'm not sure if that's the right thing to do. I am not terribly sure if the PUMS is better or if bigLC is better. I'm turning this over to subject matter experts to have a look. But my sense is that bigLC can do a better job in many cases than hot decking, because what it's doing is this multi-level clustering. It's finding it's using donors that are effectively groups of classes that could be far apart in geography, not necessarily close. So it's a little bit different from the hot decks that were actually used. Here's just the comparison of imputed values for tenure. For the age, I'm showing you summary statistics. So bigLC is imputing people to be a little bit older, interestingly, just a little bit older. Very few people had imputed sex. Okay, let's look at the race indicators. So for imputed race, imputed white status, very similar. Black status, very similar. Asian, very similar. American Indian Alaska Native, similar. Native Hawaiian Pacific Islander, similar. Some other race, similar. And then the person characteristics, once again, they're quite similar. So the reason I'm showing you this is the hot decks that were actually used to impute these characteristics in the decennial census and in the American Community Survey are pretty elaborate. And yes, the bigLC code itself is elaborate, but setting up the model was trivial. It took me just a few minutes to set up the model and run it. So yes, there's a lot of computation going on behind the scenes, but the strength of this method, I believe, is that the setup time is the setup time and the analyst time is really conserved. And there's not a lot of subjective choices that you need to make in terms of, say, setting up a whole sequence of regression models if you were going to run mice. There is some subjective choice in the families that you're using and also the number of classes that you're fitting, but there are also diagnostics that can guide you along the way. So, in my estimation, this does have a competitive advantage in terms of analyst time. Okay, so now let me just mention some extensions that are available.
Hey, Joe.
Actually, no. In the interest of time, I will. Yes, go ahead. Sure.
Yeah, sorry. I'm sorry. I'm going to ask a question
Go ahead.
before you leave the PUMS bigLC. So can we? So are we assuming that the PUMS is kind of the truth?
No.
No.
No, I'm just comparing the PUMS imputations to the bigLC imputations. So these are the values that were imputed in PUMS. You can tell which ones they are because they are flagged. So I wiped them out and used bigLC to re-impute, and then I restored them so I could compare.
Oh, okay. Well, so in a way, they're the truth.
I mean, yeah. I mean, it's, I guess, assuming that the PUMS imputation method is pretty solid, and I have no reason to think that it's not. bigLC is doing a very good job of giving you something similar with a lot less work.
Yeah, and I guess what my question I was leading to is and maybe this doesn't matter and I might be mixing things up, but it seems like it's what you're doing a good job when you is in a difficult situation where you have I mean lots of no's and very few yeses. So you have sort of this imbalance going on.
I'm sorry. Well, I mean, these are not confusion matrices.
You have to say
These
maybe
are not
I'm
confusion matrices.
Yeah, maybe I'm mixing things up, but
yeah, it's not. If it was a confusion matrix over here, this sex, the rows would be male, female, and the columns would be male, female. The rows are male, female. The columns is what PUMS imputed versus what bigLC imputed. So there were 42 cases that had to have sex imputed for non-householders. PUMS imputed 14 of those male and 28 of them female. bigLC imputed them basically 50-50.
Okay.
So it's just, this is the kind of thing that the demographers like to look at to start diving into the data to see if it looks reasonable. Let me just tell you a story. I don't think I'm violating any titles by telling you this story. Somebody recently at the Census Bureau was playing around with bigLC to see how it did for imputing the characteristics of people in group quarters. And as you know, group quarters in the 2020 census were a nightmare because, especially dormitories, students all went home because of COVID, and enumerating the dormitories was extremely difficult. There was a dormitory somewhere, I won't say where all of the characteristics had to be imputed. This was at a predominantly white private university, but the imputed values for race of the persons in that dormitory were predominantly Black, because what the hot deck that was actually used in 2020 did was it found a donor dormitory nearby, which was actually, I don't know how many tracts over, a few tracts over, maybe in the next county, that was an HBCU, and it borrowed data from the HBCU to impute the characteristics of the students in this other university dormitory. And this was something that the demographers spotted after, a year or two after the census data was published. The summaries were published, so there was nothing they could do about it. But this was an interesting test case. Unbeknownst to us, that feature was there in the data. Somebody who was playing around with group quarters imputation using bigLC, putting in tracked characteristics, found that lo and behold, that one dormitory was very different. And when they looked in the dormitory, the bigLC imputations were far more reasonable than the hot deck, because what it did was it found, it grouped together tracts that were similar rather than just looking at the nearest tract. Does that make any sense? Yeah. So that's we're seeing these minor anecdotal success stories, and we're still playing around with this, but it shows promise for being a very useful kind of imputation scheme. Let me just jump down here. This is basically the last part of my last slide. So I mentioned that there are truncated latent class models that force combinations of items that are logically impossible to have zero probability. That has not yet been incorporated into bigLC. That's coming in a future version. It turns out it's not that easy to program, but I'm working on it. The method is there. It's just a question of getting it coded. There's also the possibility, once you do that, to do what we call simultaneous edit and imputation. Given a data set with missing values and observable errors, and an observable error is a record that violates one or more edit rules, but for which you have not identified the item or items that are most likely to be wrong. It will take that dirty data set and fit a truncated latent class model and impute a clean version of the full data, multiple clean versions of the full data that conform to the edit specs. So as I mentioned, I have an appendix here that describes the main functions and my references, and I will stop here because I am unfortunately out of time, but I'm happy to keep going for a few minutes to answer questions if people would like.
Thank you so much, Joe. I don't see any questions in the chat or Q&A. Although Stas did send an email to both of us where he said you'd be excited to hear that the imputation model that you had built for NHTSA 25 plus years ago is still in production.
Very interesting.
So I guess you did find that interesting.
Yeah, there's an interesting backstory to that. So almost 30 years ago now, I believe it was 28 years ago, I published a book on how to do multiple imputation, and I had in there a technique for mixed continuous and categorical data, and it was a not too complicated but not too easy multivariate model, and I believe that's what we used for that NHTSA imputation some 25 years ago. I have since started to go and revisit the data examples in my book, and I'm finding that basically all of them can be fit very easily using bigLC. So I had a different chapter before on continuous data, chapter on categorical data, chapter on a couple of chapters on mixed data. This one model can now cover it all, so you don't have to work with different packages, different modeling frameworks.
Well, I love that. I really like how you said it's much easier to specify, the models and the inputs for the function. So I'm all for things being easy.
Yeah, and there's still, I think, work that needs to be done validating how well it works in lots and lots of examples, and I've been working through some of those. you can get into trouble with latent class models. For example, if you have way too many classes, and in your classes, a lot of them are essentially empty, but have maybe just a few observations in them. And when you start running Markov chain Monte Carlo, the parameters within those rare classes are very poorly estimated. And so you can sometimes get haywire predictions. But it turns out that once you average over multiple draws of MCMC, that crazy prediction here or there tends to get smoothed out quite a bit. So, I'm still trying to get a feel for this, trying to get a feel for what are good default prior distributions to use so that the user probably won't have to tweak them. Everything can be tweaked, but my goal is to try to have it work as reliably as possible straight out of the box.
Yeah, because if it's too difficult to kind of set things up, because I have that with another package where I mean it's fantastic, but it does make it a little bit difficult to use. The learning curve is a bit high. So there's so Yves put something in the chat.
Okay.
Yeah, he said the holy grail for simultaneous edit impute is Falegi-Holt, but seems impossible to implement usefully. I guess you know what he's talking about.
Yes. So, well, I would say Falegi-Holt is the standard. It's sort of been for many years. You could think of it as the gold standard, but I think there are possibly good theoretical reasons why you might want to consider something else, something like the simultaneous edit and imputation that you could do with this package in a future version. And I'll just give a brief justification why I say that. Falegi-Holt will take a record, look at a record, and it will see if it passes or fails edit. And if it fails edit, it will do a process called error localization, which means it will find the minimum number of fields that need to be wiped out and then re-imputed so that it passes edit. And that's not a bad standard. It means I'm going to change as little of the data as possible. However, there are examples where you can show that minimizing is not the number of fields, or if it could be changing this field or that field, you don't know which one it is. There are model-based methods that can help you zero in on the fields that are most likely to be erroneous, rather than zeroing in on the minimum number that need to be changed. And this simultaneous edit and imputation algorithm, which puts error distributions on these items, is one of those methods. Basically, it looks in the multidimensional contingency table and it sees, well, if I were to wipe out this item, how close would I be in the probability space to an admissible region of the multidimensional contingency table? And so the nice thing about latent class models is they can fit those models to the big multidimensional table without actually enumerating all of the cells. And so if you don't know what that means, I'm sure Yves does know what it means. What it means, but if you don't know what it means, don't worry about it. But there are lots of advantages to using latent class models when you have lots and lots of items.
It seems like it would be less computationally intense,
yes.
and maybe
Yes.
storage wise too.
Yes, it is, because you're never forming the big contingency table.
Yeah. Wow, that's interesting. I hadn't heard of this before. Okay. There was something else I was going to say on that, but I don't remember now. Oh, he did mention something about rejection sampling in conjunction with it.
Yes. So my yes, rejection sampling. So yeah. So right now I have this. What I'm doing now, if I have edit restrictions, that that create structural zeros in your table, what I'm doing is I'm not taking that into account in the model fitting. I'm allowing the model to actually put probability into the structural zero cells. But I do have a diagnostic that tells you how much probability mass is in those cells, the combination of all inadmissible cells in your table. It does compute that probability and it reports it to you. And so if you fit a model and you find that this model is throwing only 1% of its mass into the bad cells, then I would say you've got a pretty good fit. And then when you use that erroneous model, imperfect model for imputation, you're only going to get a few imputed values in those cells. And so if I find I'm imputing in that cell, I reject it and redraw it. And in these cases where the amount of probability mass in the forbidden zone is small, you don't notice the rejection. You're rejecting almost very rarely. And so it doesn't really matter. It's almost like fitting a model that enforces the structural zero constraints. But there are situations where the structural zero constraints will really help. I won't get into that, but I have seen evidence for certain things where you really do need them to accurately represent the relationships in your data. I'll just leave it at that for now.
Thank you, Joe. Super interesting. And whoever's left, yeah, we're getting some thank yous. I put my email in the chat. And so if you would like Joe's document, then just send me an email and I will get it sent to you. Oh, good. There's Katie too. All right. Well, thanks, everybody. Thank you, Joe.
Thank you.
And thanks for joining us, even, when you have so many other things going on.
Yes. Okay. Thank you.
All right. You take care.
Good evening.
Thanks,
Bye.
everybody. All right. Bye.